Chapter 2, Part 2, Ka, pKa, and position of equilibrium. How do we measure the strength of acids and bases? We measure it using the ionization ability. How completely does an acid or base ionize in water? Strong acids and bases completely ionize in water, while weak acids and bases partially ionize and form an equilibrium. There are 7 strong acids that you learn in CHEM. Nitric acid, sulfuric acid, perchloric acid, chloric acid, hydrochloric acid, hydrobromic acid, and hydroiodic acid. And the strong bases that you learn in Gen Chem are all metal hydroxides. You'll learn in organic chemistry that there are actually bases out there that are much stronger than these strong bases, but we'll get to that later on in the semester. So let's talk about Ka and pKa. Before we panic, there is no math in organic chemistry. This slide is only about the concepts behind Ka and pKa, so that we understand why we use pKa values to compare acids. So we're going to use this generic acid HA in order to discuss this. So if HA is placed into water, it can ionize into the conjugate base A- and form hydronium ion. A strong acid would completely ionize and turn all HA into the conjugate base A-, so there would be no HA left. A weak acid would form an equilibrium where once the equilibrium is reached, there would be some HA, some A-, and some H3O+. And the position of the equilibrium, or how strong the acid is, depends on these relative values. The more of your products that you have, the stronger the acid is. And the more of your original acid that you have, the weaker the acid is, as it was not able to lose its proton. So the formula for Ka is the concentration of hydronium ion times the concentration of the conjugate base over HA, the original acid. So thinking about these values and what it means for a weak acid or a strong acid, if you have a strong acid, you're going to have a lot of H3O+ and A- and very little HA. So that means you're going to have a big number over a small number, and you're going to end up with an even bigger number. If you have a weak acid, you're going to have very little of the H3O+ and the A- and a whole lot of the HA. So you're going to have a small number divided by a big number, and you're going to end up with an even smaller number. Now, the reason this matters is that these big numbers can be something like on the order of 10 to the 5th, right? And these small numbers can be on the order of like 10 to the -10th or something. So, and even bigger numbers in this exponent, honestly. So as you move into pKa, you're taking the negative log of these values. The negative log is just going to spit back out the exponent with a negative sign in front. So a strong acid that had a very, very large Ka value would give you a pKa of -5, a very small number. And a weak acid that had something like -10, -20, whatever in the exponent is going to give you 10 or 20 or 30 or 40, whatever it may be. So this is where these values actually come from. So let's look at that formula. pKa equals negative log of Ka. So the lower the pKa is, the stronger the acid, meaning it's easier to remove the proton and you're going to end up with a whole lot of your products. The higher the pKa, the weaker the acid, meaning it's harder to remove the proton, and your HA is going to stick around. Some examples of pKa values, just to give you an idea. HI is a very strong acid. It has a pKa of -9. So that means its Ka was something on the order of 10 to the 9th. H2SO4, sulfuric acid, is also a strong acid. It has a pKa of -5.2, which means it had a Ka value of around 10 to the 5.2. Water has the pKa of 15.7. This is kind of our so-called neutral point. Water can act as an acid or a base. Lots of things can. It all just depends on the relative acidity. But water is kind of in the middle of everything. And ammonia has a pKa of 38. Ammonia is on the kind of far end of the spectrum where it's not really an acid at all. Ammonia only acts as an acid if it's reacted with a much stronger base, and there are not that many things out there that are much stronger than ammonia as far as base goes. So ammonia would have a Ka on the order of 10 to the -38th, meaning when it's mixed with water, you are not forming hardly any of the conjugate base, if any. You are largely just keeping ammonia around. So let's talk position of equilibrium. If we have an acid-base reaction that's at equilibrium, how do we know which side is favored? So we're going to use the relative pKa values of the acids in the reaction, so the acid and the conjugate acid, to determine which side of the equilibrium is favored. Equilibrium will always favor the formation of the weaker acid, which makes sense because the weaker acid is less reactive. We are always going to favor using up reactive reagents in order to end up with something lower energy and less reactive. So for an example, we have acetic acid and ammonia. First, we need to figure out which species are our acids in this reaction. So we're reacting acetic acid with ammonia. We can figure out which one is the acid and which one is the base by comparing their relative pKa values. The one that is more acidic is going to behave as the acid. So the pKa of acetic acid is around 4.76. The pKa of ammonia, one of these protons, is about 38. So acetic acid is going to be our acid here because its proton is much more acidic, meaning ammonia will be able to remove it, whereas acetic acid does not have anything that would allow it to pull off a proton that has a pKa of 38. So acetic acid is our acid, ammonia is our base. Now on the other side, we have acetate, which is the product formed when acetic acid is deprotonated. This is going to be our conjugate base. And ammonium is going to be our conjugate acid. We also could have figured out these labels by looking at the products and determining what transfer of proton occurred. So we can see in the products that we lost this proton and ammonia picked it up to form ammonium. So we now need the relative pKa values of the two acids in order to determine which side of the equilibrium is favored. We have the pKa of acetic acid. The pKa of ammonium, one of these protons, is 9.25. So we are comparing 4.76 to 9.25. 9.25 is a higher number. That means that ammonium is the weaker acid, and that is the side of the equilibrium that's going to be favored. So this reaction moves in a forward direction, and the products are favored. Let's do another practice problem. Provide the mechanism of the acid-base reaction below and determine which side of the equilibrium is favored. Go ahead and pause and see if you can solve this yourself. Okay, so the first thing we want to do is go ahead and draw out that mechanism. Not only is it part of the instructions, but it'll also help us apply our labels of acid, base, conjugate acid, and conjugate base. So we have phenoxide here, and we have water. So phenoxide has this nice negative charge on it. That's a big hint to us that phenoxide is going to act as our base. So phenoxide is going to be able to pick up this proton. So I'm drawing a arrow from this lone pair, showing that I'm going to make a bond between the oxygen and the hydrogen from water. And then I'm going to break the bond between the hydrogen and the oxygen of water and give those electrons back to water. That's why I end up with a negative charge on my hydroxide ion. And I can see the bond that I made right here. So that's the mechanism of the forward reaction here. Now we need to determine which side of the equilibrium is favored. The pKa's are already provided for us. That's a big hint of which species are the acids, but let's go ahead and label them anyway. So we have our base. We know that it's our base because we used it to pick up our proton. That means that water is acting as the acid. On the other side, we're going to have our conjugate acid, which is phenol, and hydroxide is going to be our conjugate base. So we need to compare the pKa's of our two acids. So we're comparing 15.7 to 9.95. 15.7 is a higher number, which means that water is the weaker acid. That means that this reaction does not move forward. The reactants are actually the favored side here. So in this equilibrium, this reaction would not be moving forward. If you were to mix phenoxide and water, they would largely remain as phenoxide and water, and very little phenol and hydroxide would be formed. So for this mechanism, it would almost make more sense to actually show the reverse mechanism here. Right? And that's how we move forward in our reaction.